Okay, so I am Megan Moran, and I will be presenting with Laura Batts.
Hello.
And we are from Anderson University in Anderson, Indiana, and we will be presenting on non-realizable polynomial root sequences. Um, and so, hold on, let me hide this real quick. All right. Who wants to go? All right, sweet. Okay, so we're going to start out first with some definitions and some notation and some different tools to put in our toolbox, and then we will finish by making our claim and doing a proof over that. So first, we want to start out with what is a root sequence? A root sequence is an ordering of all the roots of a polynomial and the roots of all that polynomial's non-trivial derivatives. And this leads us to our motivating question: what root sequences are possible from polynomials with all distinct real roots? And so moving forward, we'll have some notation that will be important as we go about our proof. And this will be, P will be denoting polynomial. What degree we're in will be denoted by n. And then we will have zeros denote the roots of the polynomial. So these will be zeros of that polynomial. And then ones will be roots of the first derivative, twos will be roots of the second derivative, and so on. And then we can just generalize that by letting k denote the n minus k roots of the kth derivative. And in summary, we'll want to note that if these roots are all distinct, we will have a sequence of length n times n plus 1 divided by 2. So when we line up all of our different zeros, ones, twos, threes, etc., we will have a sequence of that length there. And then, ooh, wrong. Sorry, I'm having some technical difficulties. And so we want to look at how Rolle's theorem, which is going to be one of our main theorems here that we use to prove, how it relates to polynomials. And so we have this graph here that shows for the polynomial p, a root of the first derivative must occur between any two distinct roots of p. So this is taking that fundamental Rolle's theorem that we learned in calculus and applying it directly to our polynomials. And we see that there must be a root of the first derivative indicated there by that green x in between two roots of our polynomial indicated by a and b there. And then we want to do some more notation and understanding about how we're making these root sequences. So Rolle's theorem and these polynomial root sequences give us that for any k between 0 and n minus 2, between any two consecutive k's, there must be an instance of k plus 1. And this just means that we have to have ones in between zeros, twos in between ones, and this is better demonstrated by this example down here at the bottom. We see that 0, 1, 0, 2, 1, 0, and 0, 1, 0, 0, 1, 2, 0, 1, 0 are allowed by Rolle's theorem, whereas the sequence below that is not allowed because we see those two zeros right there next to each other at the beginning, and there's no one between them. And so we would need a one between those for that sequence to be realizable. And so an example, moving to the first example of a root sequence, is just our linear polynomial, your just classic y equals mx plus b format. And this has a root sequence of 0 because we have no derivatives, just that 1, 0 at the y-intercept. And then moving up to the second degree, we see that a quadratic has a root sequence of 0, 1, 0. And those red lines denote the zeros of the quadratic, and the orange dotted line represents the root of the first derivative. As we move to cubic polynomials with the third degree, we see that these root sequences now must contain this pattern of zeros and ones, the pattern of ones and twos, and basically just combining those two things together, we get two ways to do this. And so we see on the left a graph of 0, 1, 2, 0, 1, 0, and then on the right a reflection of that. And we're denoting the roots of the second derivative now with a dotted blue line, and the orange is still ones and the red is still zeros. And then as we move up to degree 4, we get our first instance of something that cannot happen, which is going to be denoted down there in red. And we'll get into a little bit more on the next few slides about what that is, what that means. But degree 4, we get more opportunities to combine things, but we have to adhere to the specific patterns because of Rolle's theorem. And so there's 12 different ways to do this, as we see here. The one denoted in red is one that we will consider non-realizable. And so root sequences that cannot be constructed from polynomials with all real roots are called non-realizable. And the opposite of this, root sequences that can be constructed from polynomials with all real roots are called realizable. This was first kind of established in a theorem by Anderson in his 1993 paper. He established that although being allowed by Rolle's theorem, the degree 4 root sequences that were displayed on the previous slide and listed here are non-realizable. And so a key takeaway from this is going to be that Rolle's theorem allows certain root sequences, but there are more than just Rolle's theorem that determines what a sequence is, whether it is realizable or non-realizable. And so this is just a little chart to summarize what we know about the degrees. The charts that you saw, or the graphs that you saw previously, demonstrate degrees 1 through 3 and what we had there. 4, you see that we have 12 root sequences, and then we talked about how there's just 2 that are non-realizable and the other 10 are realizable. And then as we move up to degree 5, which is the area that we're going to be interested in for our proof, we see that there is 116 realizable and 170 non-realizable out of those 286 root sequences that are established by Rolle's theorem. And then as we get up into larger degrees, we see that it just grows exponentially how many different combinations of root sequences we can have. And it's unknown what the specific counts for realizable and non-realizable are in degree 6. And so as we move into the second part of this, now that we have all our different tools to make our claim, we're going to be talking about, for a degree 5 polynomial, any root sequence containing 1, 1, 3, 3, 1, 1 is non-realizable. And this, we have not forgotten about all the other root sequences here with the 2s, the 4s, and the 0s. We just have those suppressed here because we are claiming that any root sequence of degree 5 with that 1, 1, 3, 3, 1, 1 pattern is going to be non-realizable.
Yeah, and so in order to start this proof, we had to set up our polynomial. And another tool that we need to do that is our root dragging theorem, which was also established by Anderson. And the root dragging theorem demonstrates that dragging the roots of a polynomial in a given direction has a corresponding effect on the location of the derivatives of the polynomial. And this next graph will demonstrate that well for us. And I'll have Megan go ahead and switch to that Desmos graph, which will animate it. Yeah, so we can see that as that far red right root moves outward, the second and third degree roots also move with it, or maybe those are the 0th roots. But nevertheless, as you drag one, it has a corresponding effect on the others. So we start, you can go ahead and go back to the other presentation, Megan. Thank you. So we use this in our proof. And we start our proof with the suppose by way of contradiction that 1, 1, 3, 3, 1, 1 root sequences are realizable in the 5th degree. And then using root dragging theorem, we're able to align those that 2nd and 4th degree root. And then moving on, we also, without loss of generality, are able to shift our graph so that the 4th degree root is symmetric about the x-axis at x equals 0. And then additionally, we also, without loss of generality, set our first degree roots at plus and minus 1, plus and minus k, where k is less than 1. And from all of that and all those constraints, we get that the first degree or first derivative polynomial is that 15 times x minus 1, x plus 1, etc. And then when we integrate that up, we get the polynomial that we'll be working with for our proof. So we get that f of x equals 3x to the fifth minus 5, etc. And so from that polynomial, we're able to find some really helpful information. First, we get the roots of the first derivative are that -1 is less than -k, which is less than k, which is less than 1. The roots of the third derivative are that plus and minus under the square root. And then putting all those inequalities together, we're able to establish by the 1, 1, 3, 3, 1, 1 root sequence that next inequality of -1 is less than -k, which is less than the square root, and so on. And then we do the math and algebra there, and we get that one of our constraints is that 1/5 needs to be less than k squared. So keep that in mind, that 1/5 needs to be less than k squared. And then we'll move on to our next constraint or condition that we have to meet for our proof. And this is what we call our rise drop condition. In this first graph, we see that we have our f of -1, f of -k, and so on. And in this graph, we have our 1, 1, 3, 3, 1, 1 root sequence, where those yellow lines show the ones and the green lines show the 3. And also notice that f of -1 is less than f of 1, but we don't have 5 real roots in this graph. So if we move to the next one, we have our rise drop condition met here, where f of -1 is greater than f of 1, and that has given us 5 real roots. However, if you notice, we don't have our 1, 1, 3, 3, 1, 1 root sequence anymore. Rather, we have 1, 3, 1, 1, 3, 1. And then if Megan, you could go ahead and switch to that Desmos graph, we can visualize this a little bit more with this animation. So you can see that when the f of -1 is greater than f of 1, we have 5 real roots, but when f of 1 is greater than f of -1, we don't have 5 real roots. So going back to the presentation, we can use this constraint that f of 1 needs to be less than f of -1 to do some more algebra and get that k squared needs to be less than 1/5. And if you remember what we talked about earlier with the first condition, we had showed that k squared needed to be greater than 1/5, and thus we've reached our contradiction. So this is good news. So just to kind of summarize everything that we've said through this proof, we said that we need to have two conditions met, that we need k squared to be greater than 1/5 by the construction of our polynomial. And we also need to meet our rise drop condition that f of -1 is greater than f of 1, which simplifies down to k squared is less than 1/5 in order to get those 5 real roots. And because we can't meet both of those inequalities on k squared and 1/5, we have reached our contradiction and thus proved that for degree 5 polynomials, any root sequence containing 1, 1, 3, 3, 1, 1 is non-realizable. And so the cool thing about this, so if you remember the graph earlier about the numbers of realizable and non-realizable root sequences, in the fifth degree, there are 200 some possible configurations by Rolle's theorem, but there's only, I think, 170, or there were 170 non-realizable root sequences of the fifth degree. And with this proof, we've knocked out 40 of those 170. So that's a significant amount. And we can find, we know that there's 40 because just by some simple, oh, I can't think of the word right now, or counting arguments. So this graph here kind of demonstrates that. So that for those 0 and 2 alignments, there's 2 different ways that those can be aligned. And then that 2 and 4, there's 2 different ways that those can be configured. And then same with that 0 at the top, there's 5 different places that 0 can go. So like we said, we haven't forgot about our 0s, 2s, and 4s. We just kind of suppressed them for our proof. But here they are again. And so we do 2 times 2 times 2 times 5, and we get that there are 40 different configurations possible with that 1, 1, 3, 3, 1, 1 root sequence. So that's exciting. And then finally, just some of our future work that we've kind of been working on and stuff that if you guys are interested in this, you could try and tackle along with us. But you could try looking at higher degree polynomials and using similar methods to determine what root sequences are realizable or non-realizable. And then also you can try and we try to look at counting the total number of non-realizable root sequences in degree 6 polynomials, which is kind of crazy because there's 33,000 possible root configurations. So that'd be quite a challenge. But yeah, so that's our presentation. There's some of our references. Thank you for listening. And we also want to thank our professor, Dr. Courtney Taylor at Anderson, who has helped us along the way and has been awesome and great. So thank you.
All right, thank you, Laura and Megan. We have one question from Joshua. You started out saying that you had distinct roots. What if you had repeated roots?
I'll let Megan answer this one.
Okay, so we actually have had this question before. Um, we presented earlier in the year and we got the same question. So we actually haven't looked specifically at the distinct roots, but since the question has been raised, or non-distinct roots, sorry, those repeated roots, we haven't looked specifically at that, but once the question was raised, me and Laura were kind of like, oh yeah, like that's an interesting perspective to take, and like we hadn't really thought about that. And we kind of talked to Dr. Taylor about it, our faculty sponsor. And so there's some interesting stuff there. We haven't dove into it very much. It would change things a little bit. That's what I would imagine. But yeah, it would be interesting to see what that would specifically look like with non-distinct real roots.
I
All
think
right.
too, didn't we, if we had like the graph at where k² equals 1/5, that's when we had two like repeated roots? Or am I crazy?
I am not sure.
Because I think it still holds.
I know at that 1/5 point,
Yeah,
or
yeah,
would
yeah.
not.
Because we still don't have 5 real roots there.
Yeah.
I don't know if that answers the question, but
All right, I don't see any other questions in the Q&A or the chat. Again, thank you, Laura and Megan. Oh, looks like we had a couple that just jumped in. We do have a couple more minutes. One question from Gabe, does the content of a polynomial have an influence on your findings?
I'm guessing when he says content of a polynomial, uh, like how we constructed our polynomial. So I'll answer it that way. Like whenever we go through these proofs, like we're constructing our polynomials in a very specific way, so that we can work with specific root sequences, if that makes sense. So it does have a difference on like, okay, if we want to look at a root sequence with that 1 1 3 3 1 1 pattern, we need to construct the content of our polynomial in a specific way. But if we wanted to do something more general, then you look at something like a different kind of polynomial, if that makes sense. If that didn't answer the question, try and write something else in the Q&A and we can try and answer it.
And I have another question. This is from Isaac. What inspired you to find the contradiction in your proof?
So I'll take this one. So we really weren't necessarily like, I guess, inspired to find the contradiction, but rather that was just the method of proof that we realized was going to be the best way to attack this. We kind of, Dr. Taylor had an idea of what this would kind of look like, and he knew that like this result was out there, and he, in his infinite wisdom, decided let's approach this with a contradiction. And so that's kind of how we went about it. We have kind of like a funny story about reaching the contradiction where me and Laura were both working on like separate parts of the proof, kind of like one direction and one other direction. And we both were getting like conflicting results. And we were like, dude, like, what is going on? I can't get the same thing that you're getting. And like, we have the opposite thing. And then Dr. Taylor's like, guys, like, that's our contradiction right there. And we were just like, oh my word. So it was really fun to like find that contradiction. But yeah, I hope that answers the question.
Awesome. Again, thank you, Laura and Megan. We're going to go ahead and move on to our next student presenter. If you want to go ahead and stop sharing your screen. And we're going to have Joshua Gottlieb with Pennsylvania Upsilon present next. Joshua, if you want to go ahead and share your screen.
Okay, whoops, share. All right. Anyway. All right, camera work better?
Yep,
Oh.
everything looks good.
Okay. All right. Hello, everyone. My name is Joshua Gottlieb. I'm a senior math student at Seton Hill University. I'm part of Pennsylvania Upsilon, and today I want to talk to you about the presence of integrating factors throughout differential equations. So a quick overview of and a refresher on what integrating factors are. Integrating factors typically appear when solving first order differential equations of the following type: y prime plus p of xy equals q of x. And we denote the integrating factor mu of x as e raised to the integral of p of x dx, and it's used to convert the ordinary differential equation into a product derivative. So if we multiply our ordinary differential equation by mu of x, the left-hand side collapses into a product derivative, which allows us to integrate and divide to get our solution. So the beauty of integrating factors is that they require nothing more than calculus 1 to understand. So they're very approachable by new students. Many of the other techniques that are taught in standard DiffEQ courses are utilize advanced integration techniques and are kind of inaccessible to the average DiffEQ student. And integrating factors are very versatile and can be used to solve many more difficult differential equations beyond what is normally taught. So let's go over a few of them. If you have a repeated solution with constant coefficients. So if you've got a characteristic polynomial, r of x is x minus a to the k, we can solve this using a single integrating factor, e to the negative ax. To figure out why this works, let's look at the second derivative of e to the negative axy. If we multiply out this second product derivative, we get e to the negative ax times the binomial coefficients in front of each of the derivatives of y, as well as powers of negative a. And this is exactly equivalent to the binomial expansion of a repeated root, a repeated polynomial root. So the product derivative gives us the binomial coefficients, and you can extend this to any derivative you want, third, fourth, and so on. So this will always work if you have a single repeated root. Let's take a look at an example. So an example is y double prime plus 2y prime plus y equals 0. We know the characteristic polynomial is x plus 1 squared, so we know the solution should be c1 e to the negative x plus c2x e to the negative x. Using our integrating factor e to the x, we multiply both sides by e to the x, group into the product derivative, and then we take the integral twice, which gives us c1x plus c2 on the right-hand side, and then divide by our integrating factor, which gives us the same solution that we got from the characteristic polynomial. And the really nice part about this process is that you get the powers of x that are necessary for linear independence naturally from the process of integration. What about if you have multiple solutions? So it's not just one repeated solution. If you've got constant coefficients, constant real coefficients, you can use n integrating factors where n is the number of distinct roots of the characteristic polynomial. And in order to do this, we're going to use some facts about recentering polynomials, and we're going to successively reduce the order of our ordinary differential equation. So this example, y triple prime plus y double prime plus y equals 0 is a third order ODE, and it has a characteristic polynomial of x plus 1 times x minus I plus x plus I. So the solution should be c1 e to the negative x plus c2 cosine of x plus c3 sine of x. We're usually allowed to shortcut with the characteristic polynomial because this result is proved in most DiffEQ courses using Cramer's rule, the Wronskian, and the principle of superposition. But all of those results come from linear algebra, whereas the use of integrating factors does not require reference to linear algebra at all, which some students who are taking DiffEQ courses, especially engineering students, might not even have had a linear algebra course before coming in. So what we're going to do is we're going to recenter our characteristic polynomial around one of the roots. I've chosen the root x plus 1. So we recenter it to be x plus 1 cubed minus 2 times x plus 1 squared plus 2 times x plus 1. This means we have a linear combination of powers of x plus 1. So we can use the integrating factor mu1 equals e to the x. And we multiply our differential equation by mu1 and group appropriately into product derivatives. So now that we've got all these product derivatives, we can make the substitution u1 equals mu1y quantity prime. And now we've reduced our differential equation to a second order differential equation. We're going to repeat this process until we get down to a single product derivative equals 0. The reason why this works is that because of our variable substitutions, we've shifted our original polynomial. So we had x minus I, and because we shifted by x minus 1, we now get x minus I becomes x minus 1 minus I, and x plus I becomes x minus 1 plus I. So the new characteristic polynomial has these two roots, and we can repeat the same process. So if we recenter around x minus 1 minus I, we get x minus 1 minus I squared plus 2I times x minus 1 minus I. That gives us the integrating factor e to the negative 1 minus I quantity times x. We multiply our differential equation by mu2, and we group appropriately. Then we make our substitution, u2 equals mu2 y quantity prime, which gives us a first order differential equation, u2 prime plus 2I u2 equals 0. Since it's a first order differential equation, we know how to get the integrating factor by integrating this p of x term. So mu3 is e to the 2ix. Multiplying through, we get mu3 mu2 prime equals 0. In order to retrieve our solution in y, we're going to start integrating and dividing and reversing our substitutions. So the first step is to integrate. So we're going to get mu3 mu2 equals c1, which means that u2 equals c1 over mu3, and we rewrite u2 using the previous substitution. We then integrate again, which gets us mu2 u1 equals c1 over 2I mu3 plus c2. But because our constants of integration, c1, c2, and c3 are arbitrary constants, we can allow any constants that come from the integration process to get absorbed into the arbitrary constants so that we don't have to actually worry about rewriting them. When it's all said and done, we get y equals c1 over the product of all of the integrating factors, plus c2 over the product of the first two integrating factors, plus c3 over the first integrating factor. Rewriting using our definitions, we get e raised to a bunch of powers, and we combine all the powers using rules of exponents to get c1 e to the negative ix plus c2 e to the ix plus c3 e to the negative x. This doesn't look quite like what we got from our characteristic polynomial, but by using Euler's identity that e to the ix becomes cosine plus I sine, and relabeling our coefficients, we can rewrite it in terms of the original solution that we got using the characteristic polynomial c1 cosine of x plus c2 sine of x plus c3 e to the negative x. So why do we care? The reason why we care is that using integrating factors in this way only requires calculus 1 and algebra to use. So we don't have to, and basic algebra. So we don't have to make any reference to linear algebra or higher level math in order to use these concepts. It also provides an alternate justification for just using the characteristic polynomial for constant coefficient equations. And finally, because the integrating factor can also be extended to use or to solve non-constant coefficient equations, whereas the characteristic polynomial is limited to only constant coefficient equations. So we're not going to go to the non-constant coefficient equations. So if we've got a second order homogeneous differential equation with repeated solutions f of x that are only expressible using elementary functions, so they're not power series representations, then we can rewrite, then the original ordinary differential equation has to be of the form y double prime plus 2f prime of x y prime plus f prime of x squared plus f double prime of x, all that times y equals 0. And this arises naturally out of dividing out the e to the negative f of x, integrating twice, and expanding the product derivative. So we're not going to cover that because that one's really kind of the easy case. The more difficult case is when you have two distinct solutions, f of x and g of x, which gives these coefficients for your y prime and your y terms. And we're not going to prove it, but we're going to walk through an example of how this can be used to solve the equation. So this is a rigged example, but using this example, y double prime plus 3x minus 1 over x y prime plus 2x squared y equals 0, we can solve this using integrating factors, and we don't have to resort to techniques such as power series or annihilator method or variation of parameters. So if we let j of x be the coefficient of y prime and k of x be the coefficient of y, we'll know that it has two distinct solutions because k of x does not satisfy the equality j of x squared over 4 plus j prime of x over 2. So now we're going to do some pattern matching and try and figure out what our f of x and g of x could be. So we have j of x equals 3x minus 1 over x and k of x equals 2x squared. And these match up with the coefficients that were listed earlier. Since we see 3 of x in j of x, the initial guess is that both f of x and g of x are of the form ax squared plus bx squared because the first derivative of ax squared is just 2ax. This is also strengthened by the fact that k of x is 2x squared because when you multiply two linear polynomials, you get a quadratic. So under this assumption, the fractional portion of k of x, that big ugly one with the f double prime of x g prime minus g double prime over f prime, simplifies to 4abx minus 4bax over 2bx minus 2ax, which of course is 0. And that's why this falls out of our k of x term. So using this solution, we then have to just solve this following system of equations: 2ax plus 2bx equals 3x, and 2ax times 2bx equals 2x squared. Solving the system gives a equals 1/2 and b equals 1, so f of x equals x squared over 2, and g of x equals x squared. Now, we could just shortcut here and say, well, we know what f of x and g of x are, so we know our solutions. But instead, let's walk through it using the integrating factor. Since we know one of the solutions is e to the negative g of x, one of our integrating factors has to be e to the g of x or e to the x squared. We're going to calculate the first two product derivatives, mu1y prime and mu1y double prime, and these are going to give us patterns that we need to break our original differential equation into in order to match it to perfect product derivatives. This is like what we were doing with the characteristic polynomial, except that we're not using constant coefficients anymore. So if we multiply our differential equation by mu1, and then we group it into the product derivatives, we get y double prime plus 4xy prime plus 4x squared plus 2y over here, and then we get minus x plus 1 over x quantity times y prime plus 2xy. This means we can group into the product derivatives with this coefficient x plus 1 over x on our prime term. We then make the substitution u equals mu1 y prime, which reduces our differential equation to a first order differential equation. And from there, we can get our second integrating factor using the standard technique of integrating this p of x term. So we get e raised to the negative integral of negative x minus 1 over x dx, which gets us e to the negative x squared over 2 all over x. We multiply the differential equation by mu2 and group into product derivatives. And now we're stuck with mu2 u prime equals 0. We're going to use the same process we utilized for the constant coefficients to get back to an answer in y. So we start by integrating and dividing by mu2. So we get c1, or we get u equals c1 over mu2. And then we get mu1 y prime equals c1 over mu2, which becomes mu1 y equals this integral. Now, because of the way that the integrating factor was constructed, this will always have a nice u substitution formula, which makes the integral extremely easy to calculate. You never have to resort to power series expansion or anything else. It's always a u substitution. So this gets us finally in our answer with y equals c1 e to the x squared over 2 all over e to the x squared plus c2 over e to the x squared, or rewriting it by combining all the powers, we get c1 e to the negative x squared over 2 plus c2 e to the negative x squared. This answer is equivalent to what you would get using the annihilator method or power series expansion, and can be checked by putting it into a computer algebra system such as Wolfram Alpha. So why should we bother using integrating factors for non-constant coefficients? They don't require anything more than knowledge of product derivatives, pattern recognition, and a bunch of, albeit very arduous and messy, algebra. There's also a pretty large class of ordinary differential equations that can be solved using variation of parameters or power series, but are equally ugly to manipulate with power series. And integrating factors, if you can spot the pattern, they only require algebra to use, but they don't require manipulating power series. So this example here, this disgusting ordinary differential equation, has solutions f of x equals the inverse tangent of 3x and g of x equals ln of cosine of x. Now this is a rigged example, but it does show that the integrating factor can solve what are not normally thought of as nice, easy forms. So to conclude, integrating factors can be used to solve both constant and non-constant coefficient ODEs, which makes them very versatile. They can also be used, although I didn't cover it here, they can be used to find the particular solution of a non-homogeneous, non-constant coefficient ODE of second order without having to use the Wronskian, so we don't have to appeal to linear algebra. And the integrating factor really unifies most of the concepts that are taught in a typical undergraduate DiffyQ course. So I don't want to suggest that integrating factors should replace the standard techniques, but they could be used as an alternate method of proving why some of the techniques work in a way that's more accessible to an undergraduate student who's coming into a DiffyQ course, who might not have all the necessary mathematical background to know all of the different linear algebra pieces. So thank you everyone for listening. I'll be happy to take any questions. And I also have a paper available if anyone is interested. I can just send that to you guys. Thank you.
All right, thank you very much, Joshua. Does anyone have any questions? Feel free to drop them in the chat or the Q&A section. All righty. Well, if you do have any questions, please leave them in the chat. And Joshua, if you wouldn't mind, if there is a question that pops up, responding there.
Yep, sounds good. Thank you, everybody.
All right. Well, we will now move on to our final presenter, Stephen Bates.
Kevin,
Yep. Yes.
I need to make an announcement here.
Go ahead.
These 8 presenters were all undergraduates. The next presenter is a graduate. Matter of fact, he has his PhD, so he will not be competing with the others for the prizes for the top papers. The awards committee selects the top 3, but we also have a People's Choice Award. So the you get to vote for the paper you think was best, and I'm hoping, Kevin, you have a survey you can distribute for that or make available.
Yes. So we will actually have a poll set up during the awards ceremony, which will be the last session of the day.
Okay, so that will be during the awards. So if you're trying to make notes, if you haven't printed off the program, you will have to look at that program to see which of those papers is your favorite and submit your vote when we publish that survey during the final session, the final business meeting. Okay, over to you, Kevin.
All right. So the final presenter, as Don just mentioned, is Stephen Bates, who is coming from New York Omicron. All right, Stephen, take it away.
Thank you. Thank you guys for being here. Like Don said, I'm a recent graduate from Hofstra University on Long Island. I teach in a private school in Brooklyn, New York, and I also am an adjunct professor at St. Joseph's College, which is where the New York Omicron chapter is from. So I recently completed my dissertation in October of 2020, and I looked at how the graphing calculator has an effect on middle school achievement, and compared basically student course level and student achievement level to see which of those 2 factors had a bigger impact. So before I went and dove into the dissertation process, we did have to do a literature review. And what I found was that there's been a push to integrate technology into every content area from the time of the No Child Left Behind Act of 2001 to the updated Common Core Standards of 2010, the Every Student Succeeds Act of 2015, and then the more current Next Gen Standards of 2019. And for math classrooms, that has been the tool of choice has been the graphing calculator. Different studies have found that many schools either allow or require the use of the graphing calculator in secondary level mathematics classes, but scientific and basic function calculators are used more often in lower level classes such as Algebra 1 and Geometry, and the graphing calculator is used more often in higher level classes such as Algebra 2, Trigonometry, Pre-Calc, Calculus, what have you. Teacher viewpoints regarding the graphing calculator are mixed. More than half of all teachers surveyed across multiple studies acknowledge the usefulness of the graphing calculator, but many are reliant to integrate it fully. 1, because of their lack of training in it, and 2, because they feel, a lot of teachers feel that students should learn how to do math by hand and not rely on the calculator. And they feel that way, especially in lower level classes. Another big trend is access to graphing calculators is extremely different based on school and geographic location. So public schools often require students to have them and are required legally to provide them for their students, whereas private schools are not required to do so. Regarding achievement, a giant meta-analysis showed there were no significant differences between students using the graphing calculator and students not using the graphing calculator on multiple tests of achievement. But other studies did report a statistically significant increase in mathematical confidence and a reduction in anxiety for high school students who use the graphing calculator regularly. And students with disabilities often benefit from the use of the graphing calculator, when compared to their non-disabled peers. When we visit the post-secondary land, there are very mixed results. Some studies show positive effects on student achievement when the graphing calculator is used in college level classes, yet others claim that the more students use the graphing calculator, the poorer they do in college classes. So for my study, based on what I had found, I asked two big research questions. To what extent and in what ways does the graphing calculator influence math performance at the middle school level? And to what extent and in what ways does the effect of the graphing calculator on student performance in the middle grades vary according to student achievement level, defined as high achieving or low achieving, and level of course, advanced or non-advanced. So for my research project, I completed a single group alternating treatment design using non-random sampling, which I'll explain in a minute, using a pre-test, post-test general idea. So basically all the students took a pre-test before learning a unit of study, received instruction either using the graphing calculator or not using the graphing calculator, and then took a post-test either with or without the graphing calculator. I had 106 students altogether, 60 identified as male, 46 identified as female, and one student identified as gender non-binary. That student was excluded just because I couldn't make any comparisons using them. And 33 of the 106 students were students of color. I had 7 independent variables: the use of the absence of the graphing calculator, student grade level, class level, student achievement level, gender, financial aid status, and ethnicity, and 3 major dependent variables, which was the pre-test and post-test score for each unit of study, a calculator gain average and a no calculator gain average, and then a calculator differential, which was the big variable that I used, which I found by subtracting the no calculator gain average from the student's gain average. And that's what I used basically to make all of my different comparisons. So the results from this study, so demographics come up first. Like I said, there are 60 males, 46 females. The study focused on middle schoolers. So we had 30 students participate from our Math 7 Advanced program, 40 from our non-advanced Math 8 program, and 36 students from our Math 8 Advanced program. Students in Math 7 Advanced and Math 8 non-advanced took an Algebra 1 course, and students on our Math 8 Advanced took an Algebra 2 course. When it comes to ethnicity, you can see that students who participated are largely Caucasian. So 73 students were identified as Caucasian, whereas the other students identified as different people of color. And we are a private independent school in New York City. So we are only funded by parents. We don't receive state aid or anything like that. So of the 106 students that participated in the study, 85 were considered full pay, meaning they could afford the $56,000 a year tuition. So we had 8 sixth graders who were taking the Math 7 Advanced course, 23 seventh graders, and 75 eighth graders, split among Math 8 non-advanced and Math 8 advanced. And then when it came to achievement level, which I determined based on their first semester average, we're pretty evenly split between low and high achievers. So before diving into any heavy stats analysis, I looked at different correlations to compare gain scores between tests and their calculator gain and non-gain averages. And largely what I found, regardless of their class, was that when they used the calculator on an assessment, their calculator gain average was significantly correlated to their score. And likewise, when they didn't use the graphing calculator, their no calculator gain average was significantly correlated to their gain score. So what did I find? So for the first research question, which was how does the graphing calculator affect or influence performance at the middle school level in general, I had hypothesized that the graphing calculator would help increase achievement level in both 7th and 8th grade classes, regardless of class level. Yet a paired samples t-test yielded no significant results, implying no main effect of the graphing calculator on middle school mathematics achievement. For my second research question, I had a few hypotheses. So first hypothesis was that lower performing students in advanced and non-advanced classes would see larger gains in performance when using the graphing calculator when compared to their higher performing peers. However, a one-way ANOVA yielded no significant main effect on achievement level on calculated differential score. My second hypothesis was that students enrolled in Math 8 Advanced would outperform every other student group with when using the graphing calculator. And I did find a significant interaction between course and achievement level that supported this hypothesis, yet no main effect. And my third hypothesis was that students in Math 8 non-advanced would outperform students in Math 7 advanced with the graphing calculator. And again, a significant interaction between course and achievement level supported this hypothesis. So the first significant interaction was between gender and achievement level. Overall, there was a positive effect on high achieving males and a negative effect on low achieving females. Whereas there was also a positive effect on low achieving females and a negative effect on high achieving females. So it's kind of exacerbating an achievement gap at this point within genders. The second significant interaction was between course and achievement level. So overall, everyone in Math 7 Advanced was negatively affected. Their mean calculated differential scores were both negative, whether you're a low or a high achiever. In our 8th grade non-advanced course, the high achievers were positively affected, whereas the low achievers were negatively affected, which kind of went against what I was hoping. And the Math 8 Advanced course, the low achievers were drastically affected, whereas the high achievers are only slightly negatively affected when using the graphing calculator. And then my third significant interaction was a three-way interaction between gender, achievement level, and course. All Math 7 advanced students were negatively affected regardless of gender. Math 8 non-advanced, I found that high achieving males were positively affected and high achieving females were positively affected, while their low achieving counterparts were negatively affected, showing an achievement gap within grade level within course there. And for Math 8 Advanced, high achieving males were positively affected, while low achieving males were negatively affected. And the exact opposite happened for females, where the low achieving females were drastically positively affected and high achieving females were negatively affected overall. So what does this all mean? So for the first research question, there was no main effect of the graphing calculator on achievement. Students did score better on average on these tests with the graphing calculator than without, even though those findings were not statistically significant. To calculate significance, I used SPSS, and I used SPSS to do all of the stats analysis. And the one thing I could tell from some qualitative data that I found was that it was easier for my students to solve higher order problems and to visualize functions. But that was the only real takeaway from the first research question. For the second research question, none of the 6 independent variables had a main effect on the calculated differential score, but there were some significant interactions. The first significant interaction suggested that high-performing males, regardless of what class they were in, were more positively affected than low-performing males. In contrast, low-performing females were more positively affected than high-performing females when graph calculator was used. Additionally, on average, females scored better on assessments when they were permitted to use the graphing calculator on assessments. The second significant interactions found that students in Math 8 Advanced benefited much more from the graphing calculator on average. Their mean calculated differential score was 6.5 when compared to their peers in Math 8 non-advanced, whose mean differential score was 0.47, and students in Math 7 advanced, whose mean score was negative 6.95. The second hypothesis was supported by the findings presented in the current study, and the same analysis showed that students in Math 8 non-advanced were only slightly positively affected by the graphing calculator on test of achievement, but Math 7 advanced students were negatively impacted on average. So what this shows is that there's evidence of an expanding achievement gap between 7th and 8th graders, and between high achievers and low achievers. And there's also evidence of the graphing calculator helping to expand a gender gap where females are more positively affected than males overall when using the graphing calculator. So what does this mean? So as an educator, it's always important for me to think what's best for my students and what can we do better moving forward. And the first question that came to mind is the graphing calculator the best tool of choice? With the world we live in, there's a ton of different resources that we're able to use. So I've been trying to, think about the best way to move forward in my classroom. I think it's also important that we should allow the graphing calculator as an accommodation and maybe not a requirement for students who, maybe students with disabilities or students who struggle in mathematics. And I think it's important to offer support services to lower performing students. I know that in a public school, it's a state mandate that students who are the lowest performers in the grade get support services, but in our school, since we are privately funded, we do not have to follow that mandate. When it comes to educational policy, the United States Department of Education is focused on providing high quality STEM education to all students, regardless of gender, socioeconomic status, what have you. And since the graphing calculator is suggested to expand a gender gap, its use should be questioned nationally. And it's also important to consider diversity, equity, and inclusion. Can lower income students have the same access to graphing calculators? What does equity in schools look like? We're very fortunate in my school that our students can afford to buy their own calculator, but other students elsewhere might not be so fortunate. And last but not least, for education and research, these gaps are not being closed with the graphing calculator, they're being widened. So I think that it's important to continue researching why are these happening and how do we help to close those gaps to kind of level the playing field. Some limitations that I had, it was a non-random sample because I was using students one that I taught and two were in my school. The sample was also relatively small. There were only 106 students and the groups were relatively small as well, but they were indicative of the school that I teach in. We are a private independent school, meaning we are not state funded. Like I said before, the majority of our students are full pay and can afford a hefty tuition bill every year. There was a lack of diversity overall in the sample. The majority of our participants were white. And so socioeconomic status, like I said before, most of our students are full pay and can afford tutors and any technology that we put before them. And another big limitation was testing situations. So I completed a lot of my research during the height of the pandemic. I started doing my research with the students in February of 2020, right before the major shutdowns. So I was able to get in 2 assessments with each group before school shut down, and we completed the other set of assessments during virtual learning. But after looking at the scores and doing some equivalence testing, it was found that student scores in school and out of school were relatively the same. So the results were valid. And then I offer these as following as future research ideas. Why are younger students more negatively affected by the graphing calculator? That was one of the big things that I noticed. Why are the achievement gaps and the gender gaps being exacerbated? I think it'd be pretty cool to just like replicate this study in a public school with a larger sample. I know the New York City public schools would be an amazing place to try and do this. And then possibly doing a longitudinal study where we follow some students starting in middle school and go through college and see, students that consistently use the graphing calculator versus those that don't. What does their mathematical abilities look like from, 6th grade up through freshman year of college? Ton of references here. So if you want to read any of these or read my dissertation, I'll be happy to share it with you. That's all I have. Thank you.
All right. Thank you, Stephen. We do have a few questions in the Q&A. The first, why do you think some students were negatively affected by using the calculator? Were the questions that used the calculator more difficult?
So that was one of the things we took care of before we gave any assessment. We made sure that all the questions were doable on all of the pre and post tests without the graphing calculator. I think part of the reason why the younger students did worse with the graphing calculator was basically because of maturity and comfortability with the curriculum. You know, the older students did do better, and I think it was more of a maturity thing than it was overall. Even in other studies that I read, older students did tend to do better with the more advanced class that they were in. So it kind of the results I found kind of echo what I read as well.
All right. Question from Jared. Have you looked at usage of Wolfram Alpha to reach similar results?
I have not at this point. I've been playing with Desmos a lot this year. But because of the inconsistency with being in school and out of school so much, it's been hard to get any kind of real data and any kind of findings that way. But hopefully if we can get back to normal schooling, that's definitely something I would like to play around with.
Question from Brian. Could you speculate as to why the achievement gap is widened? Do you think it is because higher achieving students are better able to make use of the calculator's capabilities?
That was my takeaway from it. I think the students in the higher achievers, no matter what course they were in, are generally more into the math anyway. So I think that they kind of pick up on the tricks that the calculator is able to help them, you know, visualize math in a different way and perform different kinds of operations versus low performing students who, by the time they get to 7th and 8th grade, might have developed some sort of learned helplessness if they really struggle, or just are not into math.
All right, next question. Did you have any problems guiding the students' use of the calculator during remote learning?
So last year I taught the Math 8 advanced classes, and I kind of scared them. I told them, you know, I'll know if you cheat, if you use the calculator you're not supposed to, and they believed me, so they were pretty okay with it. That was the risk that I had to take though with the classes I didn't teach. So based on their test scores, they were relatively consistent with what they did in school and how they did at home. So after talking to my advisor and the other teachers, we decided that since the scores are consistent, that we would take the results and it would be okay. But as to whether or not they actually followed the rules at home when, you know, they're behind a screen, that was hard to tell.
Another question from Marcus. Personally, I feel that students would benefit from spending time playing in Desmos or related softwares to see action, reaction of changing variables and graphs. But I also feel that students need to understand internally what's happening to the table of values, meaning more time putting together tables manually, perhaps. Do you feel that a mix of methods is important?
I agree with that. This year, I've used Desmos a lot more to help students kind of visualize what's happening. I not in middle school this year, but I did it with my seniors in trig graphs to kind of get them playing around with, you know, watch what happens as you increase the amplitude or you change the frequency, or play around with phase shifts and things like that. And they were able to make different kinds of connections, which was really cool that you can't necessarily do on the graphing calculator because it is relatively static. So I think that moving forward, I would definitely like to integrate that kind of program in the middle school classroom, especially in Algebra 2, where we kind of, you know, visit all the different families of functions, and hopefully they'll be able to use Desmos to kind of make the connection between the properties of different functions.
All right. Question from Catherine. When you say use the graphing calculator, does this mean that they use the calculator during the test?
Yeah, so every student during the pre-test was not able to use the graphing calculator, kind of as like a baseline. And then we split, so there were 2 sections of Math 8 Advanced, 4 of Math 8 Non-Advanced, and 2 of Math 7 Advanced. So at any one time, 1 class in 7th Advanced, 1 class in 8th Advanced, and 2 in Math 8 Advanced were either using or not using the calculator, and then kind of flip-flopped. So the classes that were using the calculator at a given time, we taught them how to do the calculations and use like different functions on the calculator to help them solve the problems. and then they were able to use the same calculator on the post-test.
All right, and then Catherine had a comment. Also, the high achieving 8th grade females did worse with the calculator. A speculation, these students understand the concepts and the calculator is a distraction.
It very well could be.
All right, last question from Brady. Would you maintain your original hypothesis statements in a public school setting or alter one or more predictions due to environmental conditions?
I think in a public school, the way I would approach this would be a little bit different. I think that I would have to consider a lot more covariates in a public school, no matter what, whether it's big city like New York or like a local public school district. I think, socioeconomic status would be a huge covariate, whereas for me, it really wasn't. And I think, ethnicity and race would also be a huge thing, because other studies have shown that students of color are often seen not as able to do mathematics, when in my experience, I've seen quite the opposite. Our students of color that attend our school often outperform Caucasian students. And I think that would be a great extension and definitely more feasible in a public school setting. I think that answered that question. I'm not sure.
All right. Those are all the questions that we have. Thank you, Stephen, very much. If you want to go ahead and stop sharing your screen, and then we've got a couple announcements from Brian Hollenbeck.
First of all, I just want to say thanks to all of our presenters. It was a lot of great talks. I hope it gives some inspiration to our other students that are part of the audience, that if you're going to be back next year for a convention, that maybe you can be in one of these seats next year presenting some sort of research. The other thing I wanted to mention along those lines is that we also have a journal called The Pentagon, and we're looking for articles for our next issue. Doug Brown is the editor, so if this was a normal year, he would actually be sitting in the back, and when you got done presenting, you could have a quick chat with him and find out more about it. So can't quite do it that way this year, but either send them just a regular chat through the Sococo or through Zoom, or email the Pentagon later. But we'd love to hear from some students and their work that they might want to publish. And even if you didn't present today, we're still, it's not a requirement to be in the Pentagon. So the other thing I wanted to mention was just let you know where we're headed. We'll have a break here in a minute, but we've got a couple of different options for folks. A few of you will be in the committee meetings, either the awards committee or the resolutions committee. In fact, I'm thinking the awards committee wants to get started maybe quicker than that. So but you can talk to Don Tosh if he wants to start immediately or not. But for the rest of us, we're splitting up into either a student session or a faculty session. And it looks like the faculty session is in the Hypatia room and the student session is in the Pythagoras room. Which, by the way, if you're curious, those rooms, along with Euclid and Diophantus, are named after what the officers were given nicknames back in the 30s and 40s, I believe. I think the president was always called President Pythagoras, and I think the historian was always called Hypatia, and maybe the treasurer or secretary were the others. So that's why we have those names today. But and those sessions, it's just a chance for members to get together and kind of compare notes. We be curious to hear your feedback on the convention, but we also just like to share ideas that work at your chapter. Maybe how you navigated the pandemic. So, but we'll be starting all of that here in a few minutes. So, and I'll turn it back over to Kevin.
Thank you, Brian. Again, if you're looking for the student session, you'll click on this icon here in Pythagoras. If you're looking for the faculty session, you'll be clicking the icon here in the Hypatia room. Looks like the resolution committee is already jumping into this room here that was formerly Office 42. And then I did create a space down here in the bottom left section that was formerly a lounge for the awards committee. But if you already have a location, feel free to meet up wherever. Those sessions will be getting started here in about 4 minutes. Feel free to head that way. If you aren't participating, feel free to kind of jump into any room, network with other attendees. If you are not in a Zoom call, you can turn on your video and audio by clicking on this drop-down arrow in the top right-hand corner. I can already see that the resolution committee in this room are all utilizing the Sococo media. All righty. Well, everyone enjoy those sessions, and we will see everyone back for the awards ceremony later on.